Okay guys, welcome back to our next lesson. Today we are on scaling and reflecting graphs. Our learning goals for today, a couple more, very similar to the learning goals in the last lesson. Understanding the effect of a scaled or reflected graph on its equation. So we're basically comparing what the equation looks like to making sure we understand what the effect it has if it's been scaled or reflected. Last time it was translated. Now when I say scaled, remember we've talked in terms of stretches and compressions in the past. So those are both versions of scaling, essentially making it longer or shorter in the vertical or horizontal direction. And then actually sketching the graph of scaled or reflected versions of the basic graphs. So again, prior knowledge first off is making sure we know what the basic graphs look like that we learned a few lessons ago. Just remembering translations because we'll throw maybe one or two of those in here as well from last lesson, and then still input-output tables and making those. So you probably still suspect that things are similar in this regard with scaling and stretching, compressing, and such. If you remember the idea that for translations, it was kind of counterintuitive, because if we added a number to y, let's say, it actually shifted it downwards. And this is going to have the same kind of thing going on. So if you notice that we've multiplied the y by 2, otherwise this just looks like the graph or the equation y equals 1 over x, which is one of our basic graphs represented there. But because the y has been multiplied by 2, instead of what you might want it to be, you might think it's a stretch vertically. It's actually going to be the opposite, which is a compression. So we're going to go ahead and dive into looking again a little bit at y. Now we will just mention here that this is compressed vertically. Okay, so this is compressed vertically. And what we mean by compressed is, we mean if we had the graph and we could squish it vertically, that means it's done that, right? And you'll see what that looks like. We can now represent 2y. We usually use the y and we replace it with n. So let's just start by looking at n equals 1 over x, and we're going to make an x, and in this case not y table. We'll do x and n, and then we'll throw the y in there afterwards. I'm going to use a variety of points here actually. Now there's one interesting point that we have to leave out. If you recall this reciprocal relationship, x cannot be 0. So we cannot have x be 0. What I'm going to use, I'm going to choose a couple very purposeful points here. -2, -1, and then -1/2, and then +1/2, +1, and +2. And when we just do the reciprocal, because right, this relationship here just simply says the reciprocal. So -2's reciprocal is -1/2. -1's reciprocal is himself. That's nice. -1/2's reciprocal then is -2, and then we get +2, +1, and then +1/2. So what we have here then is our parent graph. This is our basic graph. And I did these points just to get us actually a little bit better of an idea of the shape and kind of seeing why it behaves the way it does. And these are so interesting because it's never going to actually be able to reach 0. I almost think of this like a magnetic field that kind of pushes the graph, or you might say it pulls it towards itself, but it never lets it actually touch. Or maybe you could think of it as pushing it away, I don't know. And then there's what one branch looks like. And the nice thing is, that was the positives up here in my table. The negatives up here do exactly the same, but they're just reflected differently. So -2, -1/2, -1, -1, and then -1/2, -2. And again, if you were to graph more points, you kind of see that the shape is behaving like this. So there's our basic graph, right? What we call normally our parent. But now that we know n equals 1 over x, if we solve this for x, actually this reciprocal relationship is just switchable. So actually if n is 1 over x, then x must also be equal to 1 over n. So, and I actually made I made a mistake. Hold on, my mistake here is I meant 2y equals n. 2y equals n, I'm trying to get what y is. And so n and so y equals n over 2. So my fault. What I'm trying to do here is actually figure out what y would be. Okay, what I graphed here is as if this wasn't the y-axis, as if it was maybe the n-axis, right? So if I take all these and divide them by 2, so negative 1/4, negative 1 over 2, that's negative 1, 1, 1/2, and 1/4. Essentially, all of these have been cut in half. That's really what's happened. So this is half of itself there, and so what happens here is this has kind of been really squished down there like that. And then same here. These have all been cut in half for what was their original size. And so you can kind of see what's happened here. If you can imagine like that, you can almost imagine the origin kind of sucking it in further, right? So what does that compression actually look like here? It's literally as if we just squished it downwards, okay? So again, you don't need to technically make a table for every single one of these. It's just good that you recognize what's happened. Since the y has been multiplied by 2 right here, we know what that actually does is divide all the basic graph outputs by 2 instead. So what I did here was realize, oh, this is compressed by a factor of 2. What that means is I need to cut in half the outputs from the original parent basic graph. Okay? So there's one example. Let's take a look at another. Sketch the graph of, I threw in a translation with this one. Y minus 3 equals 2 to the power of x over 4. Now, we're going to introduce the n to replace the y here, and then the m again. So really the basic graph, the one this is based off of, is simply y equals 2 to the power of x, and that's one we have not too long ago spent time studying the shapes of these exponential graphs. And interestingly, the last one we did is not exponential, but it turns out that it still in some ways kind of behaves like that, but the shape isn't going to be exactly the same. Okay, so obviously if I just made m as my input and n as my output, if I just made an input-output table for this and did like, I think I usually do -2 up to +2. There is no domain restriction, right? There's nothing that we cannot calculate as an exponent in here. And if I was just to do the basic graph, well then this is going to give me 1/4, 1/2, 1, 2, and 4, right? If I just plug in those numbers as the exponents. But what I can do here is realize that, oh, well, if n is y minus 3, then y is n plus 3. That's again why it's shifting to the positive direction, because actually when you solve this for y, right, it's plus 3, right? So we know the graph moves up, okay? So I'm going to actually write that, shift up 3, and then I've divided the x by 4. And remember, it does the opposite of what you think. Dividing seems like it should be a compression, but it's actually going to be a stretch. And that's horizontal. So we're going to go ahead and also make sure we make note of what we think is going to happen, or what we know is going to happen, that this is a horizontal stretch, okay? And then what we can do here is we can just extend, right? And all we're doing is adding 3, right? Y is n plus 3. So if I take my n's and I add 3, well, that's 0.25. I'm going to put it as a decimal. 3.25, 3.5, 4, 5, and 7. And then my x's, remember my x over 4 is m. So if I said m equals x over 4, that means that x equals 4 times m, right? So again, that's why this actually is a stretch horizontally rather than a compression. It's because when you do this inverse relation here, x itself ends up being 4 times whatever m was, in this case when we made it into the basic one, right? So I'm just going to make all these here times 4. So -8, -4, that's 0, 4, and 8. So now what we can do is we can compare the parent, right? So if this was my parent graph, y equals 2 to the x, right? Or in this case, I guess n equals 2 to the m. What the new one's going to look like, taking into consideration the shifting up of 3 and the horizontal stretch, both of those things, then negative 8 way back here for x is going to produce now, instead of 1/4, it's going to produce 3 and 1/4, so 3.25. So what was this point back here is now here, and then this point was 1/2, but now it's 3.5, and it's at negative 4 actually now. So negative 4, and that's going to be at 3.5. Not much movement going on here, is there? Because we've compressed already something that was slow growing back here. And then 0 now makes 4, so 0 makes 4, 4 makes 5, so I'm going to go 4 makes 5, and then 8 makes 7. So 8 is going to make 5, 6, 7. So here's what this graph has looked like. We did this crazy thing where we compressed it, and so this exponential graph is now way slower growing because of that compression that I did, and I'll just kind of keep that going up there. Now, just so you remember, this eventually is going to grow and eventually shoot up and become really steep in the end. It's just we've really slowed it down a lot because of this, right? This horizontal stretch, right? And I made a mistake. I called it a compression, but what we did is instead was we actually stretched it horizontally. So if you think of this blue one, think of us pulling it apart horizontally and stretching it out, and then we shift the whole graph up 3. So this graph usually doesn't go below 0, right? But since we've shifted it all up 3, the new graph, its new boundary line is actually here at y equals 3, right? So it never goes below 3 at that point, okay? So again, we have a horizontal stretch as well as a shifting up of 3. One thing you may think about here that kind of is alluded to the fact that I accidentally said it was a compression, I was thinking of it like a vertical compression, is that for these graphs, and actually many graphs, you can really consider a horizontal stretch to be the same thing as a vertical compression. It's a little bit more complex than that, and we don't need to get into all those details, but that's just an interesting thing to note here. Okay? So since this had a lot going on, it was helpful for us to actually make the table fully out by this. But once you get the hang of doing these more, you'll kind of get the idea of how to sketch these graphs potentially without feeling like you have to make the table every time and doing it that way, right? As long as you can recognize that we've stretched it out, right? So instead of these points being 1 unit away from each other here, you'll notice these points are now 4 units away from each other. And then they all shifted up by 3 from where they were originally. And that can kind of give you some idea for how you might be able to sketch this once you get a little bit more proficient without having to do the full conversions and tables here, with just kind of getting the idea of knowing what it's going to look like. So let's take a look at a couple more graphs and just get some more practice. One thing we haven't taken into consideration is the title of this lesson also said reflections. Let's take a look at a reflection. So our next example here says sketch the graph of negative 2y equals x cubed. And again, if we thought of this as n equals x cubed, then we see this is related to our basic graph of x cubed, right? And so if I make an input-output table for that again, and again, I'm just getting us practice with this. You can still think about this without it. Notice that I've got the negative 2 there times y. So we do have a vertical compression. Remember that it's a compression. But then this negative actually reflects. And you've kind of already gotten that feeling about that prior to this lesson, but it reflects it, and we're going to say it reflects it vertically, but what we really mean vertical reflection is across the x-axis. Okay, so we kind of want to keep in mind of what's going to happen here, but then we can use this to get more precise by making our table. This makes negative 8, negative 1, 0, 1, and 8, but then remember, if negative 2y equals n, then y equals n over negative 2. So if I want to get my outputs here, I take whatever n was and divide it by negative 2 to get my y. And that's going to make for me here then positive 4, that's going to become positive and 1/2. That's still 0. But now this switches and this is negative 1/2, and that's a negative 4. So this gives me, and this helps you realize the fact that we had the negative there. The outputs were negative became positive, and the outputs that were positive became negative. And you can see that kind of means that it reflects around the x-axis like that. Okay, so anyway, -2 usually makes down here at -8, 0, 0, and let me just do this. So here's our parent graph. If I can draw it better. I'm not very good right now at drawing the graph, apparently. That's okay. Okay. And then what we can do here is just instead, -2 instead of makes -8, it makes +4. So instead of this -8, it's cut in half and reflected. So it's up here. 0 still makes 0. This still makes, actually it's going to make -1/2. +1/2 actually. -1/2 and then -4. So this has essentially become, I don't know, stumpier, I guess you could say. Again, you can just think about that we've compressed it vertically. So again, if you think about taking the blue one, flipping it across, and then squishing it this way, vertically, then that is what's going on with our purple one. Okay, let's look at our next example. As you can tell, hopefully, this one is yet another circle. So this is one where I'm not going to make a table like I have in the past, kind of like before. I want to try to identify what's going on here first, and maybe we can write it out by hand and then try to make it happen on the graph without having to make an entire table. So let's try to figure out where the center is. Now remember, the center essentially occurs at the x and y values that make whatever's in parentheses equals 0. Here we haven't added or subtracted anything, so the x-coordinate of the center is still 0, I think, and the y has been shifted though, right? So it's y plus 3, which means, let me try to get this to focus a little bit more here, which means the y-coordinate of the center is at -3. Now there's a weird thing happening here. Normally we'd say this circle has a radius of 4, which it does technically. The only thing that's weird is right here, this 2 being multiplied to x means that we've compressed it in the x direction. So basically you can think of a circle, okay, but what we've done is we've kind of squished it in the x direction, and it's going to end up still having a radius of 4 in the y direction, but it's going to be half as wide in the x direction. And we call that, you might think of it like an oval, but we usually call it an ellipse. Okay, so I'm going to write it's been compressed horizontally, and it's been compressed by a factor of 2. So knowing this stuff, now that we've just identified by looking at the equation what it's looking like, right? And remember, it looks just like, you know, the parent equation would be x squared plus y squared equals 16, but we have these changes to it. Let's just sketch the graph out then. If the center's at 0, -3, then we've got that down there. And we've got a radius of 4, but we realize that the radius of 4 only actually goes all the way out 4 in the y direction, because what would have been our radius of 4 in the x direction, horizontally, is actually cut in half. So instead of going out 4, we can go out half of that, which is going out 2. And then we can just connect this there, and there we go, we've got our graph. So now that we've gone through multiple examples here, let's just pull everything together, and then we have one more example to go over, kind of like our last lesson. So this is something you can just pause and write down yourself. It's kind of long, but it's useful to think about. Now, it's not something for you to memorize this particularly. I just wanted you to get the habit of actually learning how to write things symbolically and what they mean, and this really mirrors our last lesson. So in general, for a function y equals f of x, ay equals f of bx represents a scaled or reflected version of the graph. Okay, now technically a could also be division, because remember, if I multiply by like 1/2, that's the same as dividing by 2. So that actually has a very specific place here. So the reason why I use absolute value around these a's and b's here is because the negative has a reflection happen, and I don't want to worry about the reflection right now, right? So if the number you're multiplying in front here is bigger than 1, like 2 for A or for B, then the graph is compressed, like we've learned. And it'll either be vertically or horizontally, depending, of course, on if it's with X or Y. And then if the A or B value is between 0 and 1, so let's say I'm multiplying by 1/2, right, between 0 and 1, that's the same as dividing by 2. So that's where we have a stretch happening, right? And remember, just keep in mind it's opposite of what it looks like. And then, of course, if it's A, it's vertical. If it's B, it's horizontal. Now, if either A or B directly, not absolute value, of course, is less than 0, that just means it's reflected. If it's A, right, the number with Y, then it's a vertical reflection across the x-axis, or B represents a horizontal compression across the y-axis. So, let's go ahead and dive into one last example here. You can pause and solve this yourself if you want, but we can just work through it. If you were to just solve this equation, now notice the structural similarity here. This equation is exactly the same as that, only the x up here has been replaced with x over 3. So actually it's kind of cool. The work we do here, so if I subtract 2x there and add 7 on both sides there, right? Then I get 3x on the left side equals 12, which gives me x equals 4. Now, here's the crazy thing. I don't need to go re-solve this whole thing because all the work I just did is exactly identical. It's just x has been replaced with x over 3. So we can just say, well, skip to the end and we know x over 3 is what's equal to 4. Right? Because otherwise my steps would be exactly the same, right? Subtracting 2 of these from there and then adding 7 over there. And that's going to give me x equals 12. Now, how do the solutions compare? Oh, well, the solutions for part B are 3 times what the solutions are for part A, right? And that makes sense. Just like we did in our last lesson, if we've scaled the equation, in this case we would say, oh, well, it's stretched by 3. Right? So it does the opposite of what you think, right? And that means that our solution ended up being multiplied by 3 because of how we undid this equation. So equations are still very related, right? The solutions to an equation are going to follow the same concepts if we've had some sort of transformation of the same equation as the graphs do, okay? So that is officially it for today's lesson. And again, happy math, and I will talk to you all later.